and very difficult. So when you look at the how aspect of this, there's even theme and variations within. So we saw all the physical systems, what type of technology you could make a sensor in magnetometry or precise timing, or even measuring gravity. Those are these all can come across in many different ways. So the stuff that's typically closer to adoption is more on like the measurement side. I have a single photon sensitive camera. What clever things can you do with that? Whereas it typically gets harder and harder as we continue to more challenging quantum effects. My colleagues will talk about some quantized systems along the way. We see, once we start talking about specific controlling quantum states to be specifically doing systems to be specifically doing things, and of course when the different microscopy or whatnot that literally utilizes entanglement, the stuff where it gets touchy when we get towards adoption. Where can these types of sensors be adopted? Like I put it in kind of the top row there, maybe it's a little bit on the fourth row. What are the applications this can be? It's kind of a lot of places. We have, in the natural resources sector, start looking through the ground there. Some of these precise timing along the way. What happens when we don't have GPS? There's some of the pieces there about how we can make accelerometers or other forms of inertial navigation to be able to work around that. So definitely some large areas along the way. So when we look about the National Quantum Strategy and what Canada is sort of looking at here, it's a complex world. So as Reza mentioned here, the National Quantum Strategy, which was released probably a year or so ago, has a mission devoted to quantum sensing, to enable the government of Canada, key industries to be developers and early adopters of new quantum sensing technologies. So at the national level, a lot of these programs are working towards that mission. We also, a departmental strategy that came out recently was the Department of National Defense's implementation plan for their quantum strategy. So on the departmental side, and that sensing is also featured prominently there, where 2 out of their 4 priority areas are in sensing, quantum enhanced radar and quantum enhanced LiDAR, light detection and ranging. So there's definitely some government of Canada has put some key priorities there. To where who is either focusing, what programs in Canada are they focusing on sensing, or have put out more general quantum technology areas that focus on sensing. Of course, thanks to our gracious host, MITEX, clearly been funding some stuff along the way, supporting talent under the National Quantum Strategy's talent pillar on that side. And the research side, some great stuff from NSERC, some of their National Quantum Strategy funding on the Alliance and CREATE. Innovative Solutions Canada has been, has recently, over the last few years, called for open call for prototypes in sensing, quantum sensing. There's a government program that I think that Reza mentioned, Quantum Research and Development Initiative, seeing the different departments across Canada working together, the government researchers, to look to develop expertise across the different departments to help get them some other ones ready, and also to build some quantum technology sensing. I think a few of them are devoted to sensing along the way. And our good friend Ideas out of Defense, and particularly had this innovation network. So shout out to the regional folks who are doing some great stuff too. On the National Quantum Strategy front, under the commercialization pillar, my program here was actually funded there and effectively doubled. I put this on here too because this is one of, there's many programs out there. Even there was another one, the Applied Quantum Computing was also funded under National Quantum Strategy, but this one here devoted specifically to sensing along the way. So just a few fun facts about that. So this quantum sensing, back when I was a grad student, I organized a talk to a scientist event, and we had a bunch of grad students and researchers answering questions from the audience on sensing, communications, and computing. I had no idea what quantum sensing was. But the ironic part is ironically, my PhD was in quantum, what I would classify today as quantum sensing. So like our program here, I think it's one of the first few that's actually focused on the field of quantum sensing to gather the folks together in this regard. So this 7-year program, we're a few years in, objective is to advance the commercialization of quantum sensors with our host of many different projects, pushing towards the goal of developing a disruptive generation of quantum sensors that are orders of magnitude better. And then as you saw from my first slide there of the many different physical systems of quantum sensors, we group those into 3 themes that are all kind of working together to work towards that. And just so within the scope that we've funded along the way, just this is a kind of a representation of some of the great talent we have here in Canada. So what we are funding along, stuff a lot related to optics, to microwave, you saw this in my first slide, charge, timing, etc. And then if you kind of lump them into some of the application areas, that could be relevant either in enabling technologies or stuff that can work towards many other areas. So Canada has been doing some interesting things so far in this area. And I think as we'll hear from my other colleagues along the way here, there is as we dig deep, there's a whole lot more to be done. So with that, I think I'm going to close out for my more long-winded colleagues.
Wonderful. Yes, absolutely. Thank you very much, Amy. Thank you. It's amazing to see how many different, applications are out there for these quantum sensing technologies. And it seems like some of them are even, commercially available or near ready these days. And it's great to see that the government has different programs to support those research and commercialization in quantum sensing. We love to learn more about it. I believe we will have time for it. Thank you very much. Folks, if you have any question for Amy, please either put them in the chat, Q&A, or I don't know, if you like, you can even unmute yourself and ask your questions. But the 2 questions that I see is about presentations and the link to the video. There will be a link for sure, and we are recording this event. I will share the link with you in a follow-up email that will be ready in a few days. And then presentations, I'm more than happy to share the presentation on my tax site, but I don't know, Amy, is your presentation available to be? Okay, fantastic. So I will send that along with my tax presentation in the follow-up email to everybody who registered for this event. Wonderful. So thank you very much, Amy. My next speaker is Dr. Erica Janitz from University of Calgary. We would love to hear from a prof now that, what's happening in the academic side and what are the research, the cutting edge research that they are doing using NV centers. And she will tell us NV, what's this stand for. And yeah, please take it away, Erica.
Yes, I'm careful to define all of my acronyms. Hi, I'm Erica Janitz. I'm an assistant professor in electrical engineering at the University of Calgary, and I am potentially one of the long-winded colleagues that Amy referred to. So I'm very delighted today to share with you some of our recent work on molecular sensing using atomic defects in diamond. So I will start by outlining why diamond is such a truly exceptional host material for fragile quantum systems. So everyone knows that diamond is quite hard, but it's also chemically inert, has high thermal conductivity, a mostly nuclear spin-free lattice. So there's a very low magnetic background in the crystal, and it also has a large band gap. So it's transparent over a really large wavelength range. And within this band gap, you can have optically addressable single spin defects. And these defects are what give some diamonds their color. So for example, nitrogen doping can result in this yellow color, while the inclusion of nitrogen vacancy centers, which I think will be the topic of one of the big topics today, give diamonds this kind of red color. And the nitrogen vacancy center comprises 2 missing carbons within the diamond lattice, where one is replaced by a nitrogen. Okay, so nitrogen vacancies, or NV centers, are especially promising for building quantum technologies because they possess an electron spin degree of freedom. And this electron spin can serve as a sensor for a variety of physical quantities. The most popular is magnetic fields, and I think that's what's going to be covered today, at least in this talk. And also it can be used to store quantum information. And really important for the applications that I'll discuss today, these defects are optically active. So that means that you can actually prepare the quantum state of the spin using a laser, and you can read out the quantum state by the intensity of the fluorescence. So I've used NVs for a variety of different things throughout my research career, but the thing I'm going to talk about today is using NVs for molecular sensing. And this is what I worked on most recently as a postdoc in the group of Christian Deegan at ETH Zurich. So the idea is that we have these NV center sensors within the diamond crystal, and we try and detect nuclear spins that are within a molecule that are deposited on the surface. And the idea is that if you can detect the position of these nuclear spins, then you can actually elucidate what the structure of the molecule is. So you can look at new compounds to try and understand their structure, or you could potentially monitor reactions at the single molecule level. And already there's been some really awesome demonstrations of imaging nuclear spin clusters using the NV center to look at nuclear spins that are within the diamond. So specifically, people have looked at C13 carbon isotopes. So they've used the interaction of the NV with these nuclear spins. So this is called the hyperfine interaction, to find their position, as well as extracting the nuclear couplings between spins. And yeah, there's been some really amazing experiments on this. I think the record now is imaging over 50 spins around the NV. So it's a kind of amazing proof of concept. But going from an ideal test system within the diamond to looking at actual molecules that are external to the diamond is quite a big jump, and is very challenging. So here is an image from one of the state-of-the-art experiments where an NV was used to look at proteins that were deposited on the diamond surface. And this experiment had a sensitivity. And when I talk about sensitivity, I mean the minimum fields that you can detect. So you want to have a minimal sensitivity. So the sensitivity for this experiment was about 30 hydrogen spins per measurement. So we're still some ways away from being able to do these single spin measurements that would allow us to extract the structure of molecules. So I'm going to take a quick step back and try and explain briefly how the NV center is used as a quantum sensor for magnetic fields. So in its negative charge state, the NV center has a spin triplet ground state, and we can lift the degeneracy of the plus or minus 1 states by applying a magnetic field along the defect axis. And then we can select 2 of these states to serve as our 2-level quantum sensor. So we choose the 0 state and either the plus or minus 1 state for reasons that will become more obvious later. So within this 2-state manifold, we can create coherent superposition states using a resonant microwave field. And kind of the standout thing about the NV center compared to other spin systems is that these coherent superpositions can live for a really long time. So they can live for up to 1 millisecond at room temperature, and over 1 second has been demonstrated at cryogenic temperatures. And at the time of this publication, this was actually the record for a single electron spin in a solid. So the ground state is linked to excited states through optical transitions, and the energy splitting here corresponds to about 637 nanometers. So basically, the NV center emits red light. And for the experiments that I'm going to discuss today, we use an off-resonant excitation. So we use more energetic photons to excite to the excited state. Typically, we use just a green laser. And what's really nice about this off-resonant excitation is that it can be used to prepare So if you just shine a green laser on the NV center for an extended period of time, essentially you will prepare it into the 0 state with a pretty high efficiency. So we have some way of preparing our state. And then also to note, the MS0 state emits more photons than the +or-1 state. So we have this kind of spin-dependent fluorescence or intensity that we can use to discriminate spin states. So this is how we read out the state. However, the difference in the number of photons it emits is not huge. This is also a kind of transient effect. And finally, it's really hard to get light out of diamond because it has a very high refractive index. So if we're trying to read out the spin state of an NV center in bulk diamond, typically it has a pretty low efficiency. And the way that we quantify this is using what we call readout fidelity. So this is basically the confidence that you have in your measurement outcome. And it's typically very low, like on the order of 1%. Okay. So for molecular sensing, we want to use what we've just learned about the NV center to detect the dipolar fields that are generated by nuclear spins on the surface of the diamond, particularly those in molecules. So if we align a magnetic field along the NV axis, these nuclear spins will begin to precess about that axis, each at their Larmor frequency. And if you have a large ensemble of spins, the average magnetic field generated will be 0. But the variance is non-zero. And this is what we want to detect in our experiments. So to measure the sequence, or to measure the signal, we use what's called a dynamical decoupling sequence, which looks a bit complicated, but I will walk you through it. So the first thing we do is initialize the NV into the 0 state by shining a green laser. We then apply a resonant microwave field and create a coherent superposition. And then we apply a series of 180-degree rotations to the NV center spin. And each of these rotations is delayed by some time tau. And when this time corresponds to twice the Larmor frequency, the NV center will begin to acquire a phase that's related to the magnetic field variance generated by these spins. So we can then convert this phase into a population and read it out with our laser. The way that I had just explained on the previous slide. So the sensitivity of this scheme, or like the minimum detectable field, can be normalized to the field generated by a nuclear spin. So then you can say, like, what is the minimum number of nuclear spins that I can detect with the sequence? And this is a function of 3 experimental parameters. So D is the spacing between the NV and the nuclear spin. T2 is the lifetime of the superposition state. So we call this the spin coherence time. And then F is the readout fidelity. And this, again, we want to minimize. So first, we can try to improve the spin coherence time. And there's been a lot of work by the De Leon group at Princeton in extending this for near surface NVs. So basically, we see that this is largely limited by magnetic and electric noise on the surface. And the best way to mitigate this is to prepare a really atomically smooth diamond surface that has an ordered chemical termination. So this is something that we replicated in the Deacon group, and we're able to get spin coherence times that are on the order of 100 microseconds. Next, we want to improve the readout fidelity. And this is largely limited by the amount of light that we can actually get out of the diamond, as I said previously. So there's a big motivation to create nanophotonic structures that allow us to get more light out of the diamond. And that's what we did in this paper that was just accepted to Nanoletters. So basically what we do is create these tapered nanopillars, which act as waveguides for the NV center fluorescence. And the NVs are positioned right at the facets of these devices. So then when they emit photons, they're guided through the waveguide and they're much easier to collect out of the diamond. And also because they have these rounded tips, it's more directional. So we found that using these devices, we were able to get about a factor of 3 speed up in our experiments to have the same readout fidelity. And then finally, we want to minimize D, which is the spacing between the NV center and the nuclear spin that we're trying to detect. And there's 2 components to this. The first is the depth. So you want to use near surface NVs. However, there's also of the nuclear spin from the diamond surface. And to limit this distance, we really want to have a direct functionalization. Like we want those molecules right on the surface. So to ensure this, our team developed an amine reactive cross-linking. Sounds complicated, but basically we just expose our diamond devices to an ammonia plasma, and this deposits some amine groups on the surface. And these amine groups are highly reactive and are the basis for a wealth of attachment chemistries. So you can imagine using these amines to basically attach whatever molecule you want to the surface. And we chose as our initial test this very simple CF3 labeled molecule. And the reason why we chose this is because fluorine is not present in our experiment environment or in any of our other processes. So if we detect fluorine, we know that we've had a successful attachment chemistry. Okay, so now that we've functionalized our samples, we apply our dynamical decoupling sequence, and we see a variation in the spin contrast at frequencies corresponding to the Larmor frequency of both hydrogen and fluorine. And basically, these dips that you see here are just a function of that phase that was acquired during that measurement. Hydrogen we always see because there's always some adsorbed water on the surface because we operate under ambient conditions. However, the presence of this fluorine dip means that our functionalization has worked. We see fluorine on the surface of our diamonds. And we can actually fit the amplitude of this peak to gather some information about how many spins we're detecting. And we see that for this particular experiment, we are detecting a signal that comes from around 100 molecules. So while this is a great proof of concept, our functionalization works, we can do NMR, we really want to reduce the molecule number because remember, our goal is to go towards a single molecule, single nuclear spin measurement. And we also want to go beyond just detecting the presence or the absence of a molecule and to look at more structure-dependent signals. Okay, so this leads me to my most recent experiment where we extended these techniques to try and detect conformational changes in DNA strands. And in particular, we were interested in measuring the difference between a hairpin conformation. So here you have complementary base pairs that hold the DNA in this closed position. And this is the preferred conformation under ambient conditions. And we want to be able to tell the difference now between this open strand. And the way that we did this was using custom DNA strands that have 10 fluorine nuclei on the end. So the idea is that when you're in the closed hairpin conformation, these fluorine spins are very close to the surface and you can detect their presence. And then when it's open, they're far away and you don't see any fluorine. Right. So one critical difference between these experiments and the ones that I spoke about with the CF3 labeled molecules is that these DNA molecules are really big. So for a 5 nanometer deep NV center, you expect to only have 2 or 3 molecules within your detection volume. So already if you see a signal, you know that we're moving towards a few molecule regime. So we repeated our NMR measurements and we again see dips corresponding to fluorine and hydrogen. The hydrogen dip is very stable as a function of time, and we see quite a strong fluorine signal at first. However, we see that this is decreasing as a function of time, hinting that either the hairpin is opening through our experiments or we're somehow losing molecules. However, if we repeat this experiment on subsequent days, we often see the fluorine signal again, which strongly indicates that we are in fact changing the conformation of the molecule during our experiment. So to test whether this made sense, we did what are called melting temperature measurements. So basically you have your DNA in solution and you increase the temperature, and then you determine the temperature at which half of the hairpins are opened. So half are in the open conformation and then half are in the closed hairpin. And we see that this is about 40 degrees Celsius for this particular strand that we were looking at. And so it's not surprising at all that we were seeing these hairpins open because we have microwave heating with our dynamical decoupling sequences that is usually in the range of 40 to 70 degrees. So we're in fact opening the hairpins while we're measuring. So right now, we are kind of concluding this experiment by comparing some measurements for molecules that have different melting temperatures. And yeah, so keep your eyes peeled for this. And in conclusion, we're now able to measure some structure-dependent signal within a few molecule sample. So we're getting closer to these single spin measurements that we would like to use for structure elucidation, but we're not quite there yet. So I will continue contributing to this effort in my new lab at the University of Calgary. So there, I'm going to take a two-pronged approach. The first is rapidly searching out and characterizing novel diamond defects that have superior spin coherence and better optical properties compared to the NV center. So we can really push that sensitivity level to try and reach the single spin regime. In addition, we're going to use these new defects, some new NMR techniques, and an awesome cryogenic system that we're building to reach the single spin regime, and then hopefully look at coherent interactions between individual nuclear spins and diamond defects. And this is exactly what you need to be able to do the structural elucidation that I talked about before. So shameless plug, I am now actively hiring graduate students and postdocs, so please reach out if you're interested in any of the experiments that you heard about today. And I would like to thank all of my colleagues at ETH Zurich who did these experiments and our generous funding sources. And then I will finish with one more shameless plug for the Q-Connect event that's being held by Quantum City in Calgary, November 16th to 17th. And the idea of this event is to bring together quantum creators and users. I will be speaking again there, as will, I think, everyone else on this panel. Yeah, so keep this in mind and look at this website if you're interested in coming. Thanks.
Fantastic. Thank you very much, Erica. Thank you. It was a great talk. I learned so much, and I have so many questions.
Flatter me.
Yeah, that's amazing to see you are using basically laser, microwave, and this artificial, kind of similar to a molecule system, artificial or natural, to do quantum sensing and to measure, you know, magnetic fields and temperatures and other properties. So it's amazing. And you answered one of my questions. I was going to ask you that if you have any opening in your group, I'm sure there will be lots of, you know, people excited and interested to apply if there is a PhD position, I don't know, master's position. So great to know that you are open to accepting new students. I have two questions from audience. Let's start with those. And by the way, that Q-Connect event, folks, it's highly recommended. It's a great event to learn more about quantum science and technology, and the commercial side of it is going to happen soon in Calgary, right? So Brad is...
We're all speakers, so you get to see us again.
Fantastic. This whole panel will be there again. It's the same panel. So talking about quantum sensing. Great. Are pumped or continuous wave sources used in this type of work? I'm assuming that Brad is asking about lasers, that 532 nanometer laser that you're using. And does the birefringence of diamond impact the measurements? So would you like to comment on that, Erica?
Sure. So for the experiments I talked about today, we just use a CW green laser. We do sometimes use like shorter pulses on like the 1 microsecond time scale, but you can achieve this just with like a triggered laser or using an AOM. So it's a good question about the birefringence of diamond. In the measurements I talked about today, it doesn't impact our measurements. We're using quite thin diamond membrane substrates that are only about 50 microns thick, but there is some impact on the excitation efficiency with the polarization of the laser that you use.
And perhaps a side question, what will happen if I use, I don't know, not 532, what if I use 515 nanometer? Do I still see that red light from defects?
Yeah, so you don't need to use 532. It's not kind of a magic wavelength. It's just a cheap wavelength to use. So the absorption spectrum of the NV center is very broad, like 200 nanometers. So you can use different wavelengths to excite it with varying efficiencies.
Great. So that's where, you know, the availability of, I guess, 532 comes in handy, right? Okay, can we generate a stronger signal at 638 nanometer if we feed some portion of it to NV centers, like what's done in the laser amplifiers? So I'm assuming that Fatima's question is about like putting it in some sort of a cavity or something. Is that the question? I'm not sure if I understand it correctly.
I'm also not sure if I understand it. So I will just maybe answer an adjacent question. So you can have a much higher readout fidelity if you actually excite the NV centers resonantly. This can only be done at cryogenic temperatures, where they have a very narrow spectral line. However, so high readout fidelity has been achieved for NV centers that are deep within the diamond. The problem is that once you bring the NV centers close to the surface, they're so heavily impacted with any noise that you can't do this kind of resonant excitation anymore. So this is kind of one of the motivations for using defects that are less impacted by noise on the surface. I think that probably didn't answer that question at all, but there's
Fatima can unmute at the end and ask that question. We can, if you have time, we can discuss it in more depth. But thank you very much, Erica, for that. Could you please explain why do you use microwave in addition to, you know, the 532 nanometer laser? The 2.7 gigahertz. Where is that coming from?
Right. So they do different things. So when we're in the ground state, the splitting within the ground state is on the order of a gigahertz typically. So we can use those resonant microwave fields to create superpositions and drive rotations in the ground state manifold. And then if we want to read out what the state is in the ground state, then we excite it with the 532 laser. And then the difference in intensity gives us an idea of what state we're in.
Wonderful. And another question for you, Erica, how the Larmor frequency was tuned?
Yeah, this is a good question. So, I mean, the gyromagnetic ratio of the nuclear species that we use is fixed, but the frequency, the Larmor frequency also depends on the magnetic field. So we pretty carefully calibrate what magnetic field we're using. And the way we actually do this is by using so we have a permanent magnet on our sample and we move it around and we look at the structure of the NV center. We basically use the NV center to sense our permanent magnet, and then we know where our permanent magnet is. So we tune it with a magnetic field, and the magnetic field is calibrated using the NV. So it's a very good magnetic sensor.
Fantastic. So thank you very much, Erica. Thank you. So this is very good application of quantum sensing. Basically, as you can see, that you can measure magnetic field or even temperature. And the good thing about diamonds is they do not interact with living cells or living creatures. So you can even put them inside the living cell and do thermometry or magnetometry without killing the cell. So I have two very good questions from Ahmed and Sarah, but if you guys don't mind, I will keep it for the end, and I will invite our next speaker, David, to tell us about what his company, SP Quantum, is doing. I hear lots of amazing things about them. We love to hear it from you, David, and then I will ask those questions later. Please take it away.
Great. Thanks, Reza, for the introduction. So I'm David. I'm CEO and co-founder of SP Quantum. And today I want to chat a bit about the work that we've done, but also a bit of my journey in startup creation and how my tax has helped in getting there, actually. So yeah, SB Quantum, we're about quantum magnetics to see the unseen. So leveraging kind of this invisible force of magnetics that's everywhere, but that maybe not everybody understands, unlike photons, which we use to play with or interact with around us. Magnetics is kind of this unforeseen magnetic force, but can have lots of application, as you'll see. Our 10-year vision is that in 10 years, our world magnetic maps created with quantum sensors will be in every cell phone. Basically, every time you take your cell phone and look at the blue arrow to know where to head left or right, it's generated by comparing a worldwide magnetic map with magnetometers in your cell phone. So actually, we're currently fitting our quantum magnetometer technology into a CubeSat in order to build these type of maps. So down the road, we'll be in everybody's pockets. More immediately, we're not only focusing on developing this diamond-based magnetometer technology, but also leveraging advanced interpretation and noise mitigation techniques in order to be able to deploy our technology into various platforms, ranging from drones, airplanes, and satellites. Getting there was quite an adventure, I would say. So when you launch a company, you have to go through the customer discovery phase. We went head down into this process through the Creative Destruction Lab quantum stream in Toronto. And what you get asked all the time is, where's the 10x? What's the 10x? I want the 10x so that people can change technology and adopt the technology. So we went around, poked a lot of people on where they use magnetometers, what end use case they see. We even chatted to, my favorite example is this aquaculture application that's on this slide. And basically their challenge was, they have trouble counting the number of fish they have in this pond. And they were like, can you measure it with magnetic field? And we're like, yeah, fish are not that magnetic, but like if we insert a little chunk of metal, maybe we'll be able to detect it and track it. But in the end, we did the calculation, the napkin calculation, and the chunk of metal was a bit too big to fit in the head of a fish. So eventually that one didn't materialize, but it was still very insightful to learn about this use case. Other people told us like, oh, I'm looking to reduce the amount of time people spend inspecting infrastructure. Some people told us, well, I don't care about new technologies until like regulation asks me to do it, or if you're going in full detection into the ground, well, the laws need to be there for me to care about it. And so some people told us, oh, this could be game changing, let's say in detecting submarines or in the exploration and mining. So going through this process, so my background is a PhD in quantum physics, I would say was quite insightful and great from a growth perspective. So in the end, what we funnel down to is magnetic data as a service. And what we mean by that is that not only we want to focus on building the quantum technology, but magnetic field sensors actually are seen as a commodity. They provide limited amount of information. So we have to fuse that with some interpretations or novel use cases, so that we're not stuck into the magnetometer as a commodity game, which can be quite tough. And we've identified three main market verticals. First, one of them is exploration and mining. We need to find 300 to 400 new mines for the critical minerals we need to build the batteries. So there's a big pressure on the exploration, setting up these new mines, providing good data. Magnetics turns out is the first sensing modality that's used by geophysicists and geologists in order to kind of steer the exploration process. And we're developing a solution which provides 5 times more magnetic maps so that we can be more targeted into the exploration process and have less environmental impact, have a greater probability of success in establishing a mine. Second pillar is defense. Of course, like submarine warfare, detecting submarines is a big topic since like the Second World War. What can we do differently actually is going not only to detection, but also classification of what we're measuring. So that's something we're actively pursuing, not only in the Navy space, but also in the special operations space and kind of intelligence and surveillance. Last pillar, which is the one that we're putting the most effort lately, is the space stream. So as I mentioned, these worldwide magnetic maps are used in every navigation system, in every cell phone. So we're actually part of a program to build these next generation magnetic field maps, and down the road, maybe looking at the magnetic-based navigation. So on that topic, a few more words about this MagQuest challenge. That's a challenge that started 3 years ago. Initially, it was they asked for a 4-pager for new ideas on how to generate these kind of magnetic field maps, and phase by phase we advanced the readiness of our solution. And it's really an interesting program for us, since the program metrics are quite easy from the point of view of developing a quantum technology. So we're in the nanotesla range, not femtotesla crazy type of requirement. So it was really it is a really great challenge for us. And we're basically building on 2 main innovations. So CubeSats, which have truly game-changed the space, how sensors and how solutions are deployed in space. ML for compensating for the CubeSat magnetic signal, and this novel diamond magnetometer technology. You can see here a red diamond glowing following green excitation. We just completed independent evaluation by NASA. We put our sensor into this big coil facility that's the size of 3 buildings, and basically they characterize linearity, orthogonality, everything from a sensor, a magnetometer point of view, not only like a technology working in the lab and measuring something, but more from a systems approach. On the magnetometer, so you already know how that works. Thanks, Erika, for covering that. Again, glowy diamond picture, different angle. You can really see the glow from the naked eye because we're using diamonds with ppms of the concentration of NV centers, so very high density. Through the years, we've roughly gained factor 10x on the device performance. We have a dedicated electrical engineering team, with whom we've developed a portable system. So we design our own electronics, we have them fabbed elsewhere, and we bring everything together and kind of add our secret sauce on how to extract efficiently the magnetic field vector. And one key factor, like people like to rally to numbers, and usually they adopt the sensitivity, but in our case, accuracy. So the true value of the magnetic field that you measure is as important, if not more, especially for building the world magnetic model. And right now we're down to the nanotesla range. So it's been quite a learning for me from the point of view of being a physicist in the lab, working closer with the electrical engineers and even from my postdoc and with interns. Electrical engineers as interns add like tremendous input into shaping a solution. We're about to commercialize our first diamond magnetometer. It's portable now. It fits into this casing. It's roughly this size. If you can see my hands, it's really portable. It fits in a CubeSat, and really the challenge there again, measuring with 1 nanotesla precision. The magnetic field is roughly 20 ppm, so crazy accuracy at that level. At that level, any metallic part will kind of screw up your precision. And we had lots of support. I think that's one thing for maybe the students in the audience. Having a collaborative mindset was really helpful for us. So we have a collaboration with Natural Resources Canada. It turns out that they've been involved in in the design and the commissioning of various magnetometer technology by GEM Systems, but also CAE, who have the benchmark magnetometer for defense purposes and anti-submarine warfare. So there you can see our instrument being wiggled around by one of our interns, and there are some coils here to again characterize the performance of the device before we head to independent evaluation by NASA. So it's been really fruitful. I want to switch gears now a bit more to the journey and the key skills that I foresee in starting a business, or even like in looking at other professional perspectives outside of academia. So it was quite of a process for me. At the end of my PhD, I knew I didn't want to become a prof. So I was like, okay, what's next then? And I was interested in startups. So I followed a quick course about the startups 101, I would say, looking at the case studies of what business worked and didn't work, and I found that pretty fascinating. So I went back to the lab and told myself, okay, if I want to convince investors or grant agencies to give me money, I need IP. So I found a patent to work on in the same research group to kind of get up to speed with what is the process, then filed a patent as a sole inventor at the university. Got involved into a bunch of grant writing, both at the university level, but also from a company perspective. They didn't work at first, had multiple failed applications, but it was part of the learning, I guess. And also I did accelerate my tax with a company in the field of environment, looking at how we can use magnetic fields to find faults in buried structures that hold contaminants. So quite a busy end of PhD, but at the end it bared its fruit. What really made the difference for us is really embracing the open innovation challenges in order to get closer to end users' needs, which can be quite a challenge coming from academia. You're a bit more remote from these applications, or what are like the key problems that the companies face or society faces. So already mentioned the environmental segment. So we had like magnetometer arrays towed by a robot scanning structures in the ground. Then we had support from the Ideas Innovation Program in order not only to develop the hardware, but also the compensation and interpretation algorithms. And here you can see kind of these are two interns in our elevator. And we had a backpack with an array of quantum sensors versus classical sensors. And with quantum sensors, we show that we can detect in real time where the elevator is. So kind of going beyond just, oh, I'm measuring something and somebody else got to figure what this means, but really going the extra mile to give information that matters to the end user. And finally, the MicroQuest program, I think I covered pretty much that one, but just to say, these innovation programs, it's worth trying a while. It began with a 4-pager. Realistically, I never thought I would get in at that point. We were still very early stage. We got 25K US, and now it's become a $1 million plus contracting opportunity with the American government. Our team, just to show we love engineers. We have engineers in-house that remind me that we need 3 engineers to tame 1 physicist. So we're kind of aiming for that balance in some sense, but we also have lots of, we have a few data scientists in-house and software engineers. These matter. Code is everywhere now. So even if you're in physics, that's a key skill to have. And we love interns. So we started with interns. We still have 4 to 5 interns per semester. My tax interns to get a deep dive and leverage the expertise of graduate students in order to push some aspect of technological development. These are our values. I like Lego. I think this shows us perfectly the mindset of people working at SBQ. So we're looking for people who are collaborative, dynamic, innovative, transparent, and not afraid to say when they made a mistake, and that are interested in looking at the user needs. And key skills that we're looking for, usually experience in experimental physics or engineering is, of course, a key skill we're looking for. Coding skills, like I just mentioned, code is everywhere now, and it's very collaborative. So get your GitHub skills up to speed. Creativity and agility for a startup. Stuff can change over the scale of 1 week, so you have to embrace the unknown. That's a key mindset point. And finally, being able to work in teams. So if you have any opportunity to work as part of a team and to collaborate with a multidisciplinary team, that's really great. So yeah, that's it. That's about SB Quantum. We're always looking for interns, and we also have full-time positions open as project managers, product manager. Yeah, we're building the next gen magnetometry from Quantum.
Wonderful. Thank you very much, David. Yes, thank you. Thank you. It's amazing to see and hear about your amazing journey from being in the grad school and postdoc and everything into becoming a founder, a very successful startup that we are hearing about it here and there, and now you're working with NASA. That's amazing. And also you went through CDL program, and you're recommending that. So that's all good and great. And I have lots of questions, especially about the entrepreneurship side, but I want to keep time for Martin's talk as well. I'm going to just ask Ahmed's question, since you mentioned mining, and you can, there are some applications in mining. Can you please comment on that and elaborate how we can use this quantum sensing technology in oil and gas exploration, and on the mining side, how we can use that and how it works relative to all these, legacy technologies that are available in toolkits for mining, perhaps oil and gas exploration?
Yeah. Good question. So magnetometry isn't new for mining. It's been used for decades, basically, for exploration, mainly from an airborne perspective. Total field magnetometers, whereas we measure the vector magnetic field with our technology. Yeah, so there's a big push to move towards drone deployment. So there's more and more requirements to have small and precise magnetometers, and that can understand kind of magnetic contaminants coming from platforms. So that's where we can make a difference, and also the fact that we're building arrays of these vector magnetometers in order to generate 5 times more magnetic field maps and have a better understanding of what's shallow versus deep in the ground, and be able to image smaller faults into the ground. That's kind of what we can do differently. The existing platforms that generate these type of maps are made of squids, so superconductors, so very difficult to deploy and take a lot of resources. On the oil and gas side, turns out oil and gas is not magnetic, and is not linked to any magnetic geology. So mainly the application there is from a navigation perspective. How can we orient better the drilling underground? So of course you need some way to navigate underground, and for that magnetic field maps are being used.
Fantastic. And are you guys doing anything specific right now for mining, or
Yeah, I didn't show pictures. I should have, but well, this is us with the snowshoes. So we had a survey with the Geological Survey of Canada, and we went also to Raglan in Nunavik, so upper Quebec, snowmobiling with our technology and generating these magnetic field maps. So yeah, we're at the pilot stage and looking for more collaborations and deploying the tech.
Mm-hmm. Fantastic. So one last question before Martin. Erica showed us that we need microwave generation, manipulation, reading, lasers, green lasers, and NV. Put them all together and then do the manipulation to read. So did you guys put everything in that one small box that you showed us? Is that what Speak Quantum is about? Miniaturizing and integrating all those components?
Yeah. There's only a power feed and data feed. Like everything fits in there. We generate microwaves, laser pulses. We do the readout, so that was part of the big challenge. Just working with the electrical engineering team and listing the requirements and sticking to them. Like our first prototype, when I was fresh off the PhD. I was like, oh, let's do pulse shaping, and we like spent 4 to 6 months developing this pulse shaping capabilities, and in the end, it was like the least. It should have been the least of our worries. We had stuff to work on that would give orders of magnitude increase in performance instead of percent. So.
Fantastic. Thank you very much, David. Mojtaba has a question, but I will keep it for the after basically Martin's talk. Martin, please take it away. It's all yours. Thank you, David.
My pleasure.
All right, give me a second to get my file going. Okay, see it all good. Well, thank you, Reza, and my thanks for inviting me to present here. We're going to take a bit of a fork in the road, but well, I feel I was planning on taking a fork in the road, but now I feel like I'm doing a bit of a summary of all the other talks. So Reza asked me to talk about the ecosystem that we have here in Canada to support, quantum discovery, research, entrepreneurship, and all that. And I figured that I was in a good position to talk about not only what we have, but the importance of what we have and the beauty of what we have. So I started my career as a PhD student in physics in an experimental lab in Waterloo. But I bifurcated quite early outside of academia, a bit like David. I felt professorship was not really for me. So hats off to Erica. It takes a special kind of people to be professor. But I spent a good chunk of my career being a promoter of quantum technology. So in the early days, I was essentially promoting what will come in a future, in a certain future, what the impact of quantum technology is going to be, the importance of curiosity-driven research to prepare for a future. And then, I find myself, 10, 15 years later, where now I'm no longer talking about what can quantum technology do, but what they actually do today. And then for the past couple of years, I took a real turn towards some people call it the dark side. I created an investment fund called Quantaset, which focus on investing in early stage quantum startups. Mainly in Quebec, but we're also looking at the rest of Canada and the rest of the world. So I'll give you a bit of a perspective from a business/investor point of view of the opportunity that we see. And then what we're looking for in quantum technology. So I'll focus mainly on quantum sensors, but Amy kind of talked about this right at the beginning. We often put the quantum technology in 3 buckets. There's quantum computing, quantum communication, quantum sensors. We also typically add 2 more buckets to this, which are quantum materials, which are very enabling. That's what will allow us to kind of take a lot of those technology outside the lab. And we often talk about enabling technology. So think of all the technology that we develop so that it's possible to create quantum technology. You can think about optics and photonics, ultra-stable lasers, very specific electronics, even cryogenics, that sort of thing. So that's kind of where we look at it when we talk about investable quantum technology. So if I'm looking at just the market opportunity, so first of all, if you look around to find numbers on the market size, they are all over the place, okay? Because let's be honest, we're looking at a crystal ball nobody can predict really what's going on. You know, never forget that in the early days of the computer, we were predicting that there would be a market for 5 computers. I have 5 just right here in this room, okay? So take all those numbers with a grain of salt, but I think the relative proportion might be roughly okay. So there's a huge potential for quantum computing, quantum communication, big, a little smaller, quantum sensor as well. So, you know, some people could argue that quantum smaller might be the smallest market, but personally, I'm still under the impression that I think we're downplaying the importance of quantum sensors, and also, let's be honest, they're often the forgotten quantum technology cousins of the other one. So that's why I'm passionate about talking about quantum sensors. So kind of a recap of what Amy talked about. Quantum sensors have many applications, right? I was just looking the other day. If you look at new smart cars. A smart car nowadays that have some self-driving capabilities, you have about 150 sensors just in a car. So let alone exploration, space exploration, and all this. And some technologies are mature, some technology already exists. Some technologies are being developed, like, you know, David's company, and some technologies of quantum technology has been around for 50 years. You know, an MRI machine, it's a quantum sensor that's been around since 1970 something. And, you know, at some point we all got our head stuck in one of those machines. So all this to say that what's the beauty of quantum sensor is that we don't know where they can be applied, but I mean that in a good thing, is that we don't know in the sense that they can be almost applied everywhere. Again, just showing you a bit, so here the 2 graphs look the same, but look at the numbers. Here, although I'm you know, myself, I have a background in quantum, I work in quantum all my life, I have quantum literally tattooed on one of my arms. I'm the first one to say that if you believe that quantum is the solution to everything, you're wrong. You don't need quantum for everything. And that's what this graph is kind of showing, right? Yes, quantum can significantly enhance our capability for sensing, but we don't need an enhancement of capability of sensing in everything, right? I have a smart thermostat at home, which gives me temperature of my house to 0.1 degrees. I don't need to have, you know, to go into the ppm of degrees to know the temperature of my bedroom. So, and here we sort of have a relationship that maybe quantum sensors will be useful for, you know, less than 10%, 5% of the market. Still, it's an important market. And the place that we, as investors, we liked a lot is that the growth of that market, like the CAGR, as we call it, the compounded annual growth, is significantly larger of that than traditional. So there's a real opportunity there. So, and also here I sort of, I took a page from our pitch deck, from our investor pitch deck, which sort of show how we were planning to diversify our investment portfolio. And it turns out that the risk level and the potential of return on investment in quantum technology kind of diversify itself naturally, right? So everyone talks about quantum computer, how cool they are, how they're going to change the world. Well, to be fair, there's a big question mark on that one. But if we build a at-scale fault-tolerant quantum computer, it will become a $1 trillion business overnight. Okay, so there's a huge potential, but the risk is massive. Quantum sensors, on the other hand, they are, so, you know, now David and Erica is going to look at me with angry eyes, but they are engineeringly talking a little bit simpler. I'm not saying that they're easy to make, but in terms of system, a tiny little bit simpler. So we can potentially commercialize them in a much shorter time scale. And, you know, SB Quantum is a good example of they are commercializing it right now. But the market might be a little smaller. So it's a trade-off, right? Less risk to get into that business, maybe a smaller trade-off, a smaller market, but you can still have some really nice and good business that are worth investing in. So that's sort of, it's just a bit of the wrap-up of where we see the market and where we see the opportunity as investors. And for investors like us at QuantAsset, which were one of the rare, and if I count real quick in my head, there's only 5 or 6 funds in the world that are 100% focused on quantum. And if you look at all the other funds that are looking at quantum, typically they'll be looking at quantum computing because it's cool and it's a big play, and then they can put on their website that they are an innovative investor. Well, it's good for us because then we're the only one looking at the quantum sensor and grabbing this opportunity. So it's more for us. So now I want to take a bit of a fork because Reza asked me to talk about the ecosystem we have in Canada, and I'm talking in the lights of starting a company. And David went through a lot of those things already, and I'm just going to take more of an abstract approach. The first thing that I want to tell to the people here in the audience that might be thinking about entrepreneurship or starting a company, the typical approach to start a quantum business will often start in the lab. Okay, let's be honest. The idea of having a book written about you in 10 years that you started alone with your brother-in-law in your garage and now you're leading $1 billion company is probably not going to happen in quantum. You need a lot of investment, lots of infrastructure, lots of expertise. So typically you will start out of a university lab. So you start with a theoretical idea or an idea that you're exploring that you saw in the literature. Then you'll build a prototype, right? A lab that has got wires everywhere. You'll see tinfoil, duct tape, but it kind of works as long as you don't breathe on it. But now you've shown that your technology works. But if you want to commercialize, you got to turn that into a product, make it in a robust fashion that, that can be sold and moved. And so this is typically what you imagine, or what a lot of people imagine. What is this start a company? But sometimes we forget that building a product is only one part of having a business. Somebody needs to buy that part. Otherwise, if you don't have a market and if you don't answer a market problem, you're just doing a cool experiment that nobody will buy except you. Okay. So, and that's often coming from a scientific background. That's often where we get lost. We think that because our stuff is so cool that everybody wants to do it. But you know what? If your stuff does not solve a problem, nobody gives a hoot that it's quantum or not quantum. That's the way the market works. So never forget that you need to identify your market, and then you need to answer a problem that nobody else has answered. The beauty with quantum sensors is that they're not really, quantum sensors are not trailblazing a new market like quantum computers or quantum communication do. And I don't want to sound diminutive here, that's not the intention at all, but they essentially come in as a new, better, stronger, faster, more sensitive version of, in most times, of sensors that already existed. So the market is typically fairly well identified. You have a lot of data to study your market and understand where you can fit in. Here I just found a typo. The third one is like, there's known players. Typically, for example, again, if I take SB Quantum, he knows who the competitors are. He knows who he's going against, and competitors / potentially partners, but it's well identified. And also the nice thing is, for sensor, you don't need to say that it's quantum. Because saying that your technology is quantum, it's a double-edged sword. Some clients might find it really cool and might go for it because it's quantum. Some client might find it off-putting because their first reaction will be like, it's too complicated and it's all theory and blah, blah, I don't want to hear it. At the end of the day, you don't sell quantum, you sell a solution. And whether your solution is classical or quantum, nobody cares. You sell a better solution. So those are the advantages. There's a downside to it, is that you're starting way behind, because classical sensors are extremely well developed. They can make some really good technology. So you have a lot to show before you can offer a competing business. Also, they might be more expensive because you don't have an economy of scale just yet. You're at the beginning of your journey. You don't create sensors by the thousands. You create them one at a time, or a couple of people just soldering stuff in the lab. The competitors are usually well implemented in the market. And the other side, I kind of mentioned that before, it's not as sexy as quantum communication or quantum computing, according to the media. Personally, I think they're completely wrong. But quantum sensors maybe get a little less attention, or less attention than they deserve. So they might not have as much place in conferences, in media, and that sort of thing. So it might be a little harder to sort of get the message out. So we talked about building companies. And I kind of mentioned that a quantum company does not get built by one person in a basement or in a garage. So you need a whole ecosystem. And I think this is one of the strengths that we have here in Canada, is that we started building that ecosystem really early on. And an argument could be made that Canada was probably one of the first nation, or maybe even the first nation in the world, to really invest in a full ecosystem from research to commercialization, even before we could see that there was a real commercialization potential. We put all the place. From research training, helping the entrepreneurs, funding, and not just research funding, but funding for startup as well, for partnership, infrastructure, research infrastructure, ecosystem, and this kind of a concept slide. But let me talk about some of those circles in concrete. Let's talk about research and training. So, I mean, I'm not gonna, it's not something new to say that Canada typically, hits way above its weight when it comes to fundamental research. So we are stacked in academic research in quantum. Whether we think of the Institut Quantique here, where I'm sitting in Sherbrooke, the Institute for Quantum Computing in Waterloo, UBC, Toronto, and there's a bunch of other universities that have maybe smaller effort, but effort nonetheless. I'm just showing like the big ones. So we have, if I do a quick estimation, probably over, I don't know, like over 1,000 quantum researchers in Canada alone. Well, we're a small country. In terms of infrastructure, same thing. Whether we talk about clean rooms, cryogenic lab for rent, shared facility. So you have some, again, here in Sherbrooke, there's some in Waterloo, there's some out west. So there's no excuse to not have access to the facilities that you need. We even have like a Pink Square, which is a new HPC facility that we open here in Quebec that marries both classical and quantum computing for supporting that, not only the research, but companies that want to start investigating quantum. Also, we have full-scale ecosystem in some different places. Here in Sherbrooke, we have something called District that's built, that's supporting that ecosystem. There's a Quantum Valley in Waterloo. Now, Alberta came up not so long ago with that the Quantum City, which they're building, and as far as I'm concerned, going very well. The CFAR, which is a regroupment, there's many different streams, but there's a regroupment of all the quantum researchers. So Quantum BC. So there's national efforts and there's provincial effort. So we're very well installed. A bit now, the money, right? Money is extremely important for the fundamental research, but also for creating a startup, because entrepreneurs need to put food on their table, and the whole concept that entrepreneurs works 28 hours a day, 8 days a week, and eat just 3 packs of ramen. We're past this time. Okay, we believe that they need to be well fed, well paid to move forward. So we're lucky here in Canada that governments, the federal government and provincial government, have put many programs to support fundamental research, technology transfer, support young enterprise to get started, to academic research to do collaboration with companies. So there's a lot of government funding that is non-dilutive, meaning that it's free money, which means that you get money and you don't need to give a part of your company in exchange. This is beautiful. Also, the government money just bring you so far, right? It's really good to get you started, but at some point you need to go and then start growing and growing fast. This is where the private funding comes in. This is where companies, funds like mine, Quantaset, comes in. There's also the BDC, the what is it in English? The Development Bank, Business Development Bank of Canada, that has a fund specifically for deep tech that has a big quantum component to it, Quantum Valley Investment. So Quantum Nation also, which is a large international fund that have a significant presence in Canada. So those are the venture capital that are there to sign the big checks, to really bring you to the next part. But that money is not free. It comes with equity. So we become essentially part of your company. But all of those funds that I've worked there have quantum expertise. So they are smart money. They're people that can invest in your company and support you and help you grow. And speaking of growth, we also have a few incubator and accelerator here in Canada that are specifically, that have specific stream to support quantum companies. If you talk to some companies, some young entrepreneurs that went through incubators with a company based on quantum technology, the first thing they'll tell you is like, they had no idea what I was doing. Not no idea that I was doing in terms of science, but in terms of the business model of quantum company is extremely different than your typical business going in an incubator. Typically in an incubator, the first question they ask you is, what's your revenue? And typically with quantum, be like, well, I'll tell you in 5 years, because most quantum company are pre-revenue and very often pre-product, which kind of shakes completely what we do in terms of commercialization. So your typical incubator, not that they're not good, they're just not prepared for that reality because they don't live it. So at Lassette, example in Sherbrooke, Creative Destruction Lab, Quantino, CDL is in Toronto, Quantino's in Quebec City. We have quantum expert there, people who lived it, people who comes from the quantum industry, who can understand the reality of a quantum entrepreneur. So all of this to say that quantum sensors offer a great opportunity. There's tons of meat on the bone to get into the market. And if you want to go the entrepreneurship route, personally, I think that Canada is one of the best places in the world to do that because of all the support that we have from the different level of government, the private, the infrastructure. So it's a good place to launch into the business and venture.
Wonderful. Thank you very much, Martin. Thank you. And we stop with that. We went 4 minutes over time. And thank you to all our audience who stayed with us all the way to the end. Thank you, our speakers. This was amazing. I will share with you guys these presentations in a follow-up email. And by the way, I saw Megan put the link to that event coming up in Calgary. Please check that link. It's highly recommended event. Join if you can. Thank you very much, guys. We learned so much about quantum. Yes, excellent panel. Quantum sensing, especially Martin, and we learned about all these available resources. If you are thinking like David, that, hey, I don't want to stick to academia, I want to go start my own journey in life and my own business, there are available resources that you can take advantage on both sides of the things, on Martin's side and on Amy's side, the government, the private sector, there are so much help available. Contact us if you need to connect with any of the panelists, if you want to learn more about quantum ecosystem across Canada. Thank you very much, guys, and have a wonderful day. That's a wrap for today. We will have more events coming up.
Thanks, everyone.
Thank you.
Enjoy.
Thanks, Reza, for organizing.
Of course.
Thanks, Rez.
My pleasure.